When we talk about electronics and electrical devices, the thing that's on our minds most is energy. How do they use energy? How do they transform it into useful work? And something I bet you know is related to that is a concept called voltage. You've probably heard of high voltage. You probably know that various power supplies have different voltages. You may be aware that different countries supply electricity with different voltages. And I want to make sure we understand what that means. The real physics word for voltage is electrical potential, which sounds a lot like electrical potential energy, but it's slightly different. Voltage is the potential energy per charge. Depending on what class you're in, you might write it as PE over Q or U over Q. So why would we care about the potential energy that each charge carries as it moves through a circuit? That's what this video aims to explain. We're first going to look at the various voltages that you might encounter in your everyday life. We're then going to try to define this and explain why it's important. So here's some various batteries, and it's informative to look at the different types. The 9-volt battery clearly has 9 volts. But the other two, the D and the AAA, I don't know if you've ever looked at them, but they actually have the same voltage, 1.5. And that means electrically, they're very similar, although you use them in pretty different applications. So the D we usually use in devices that use a lot of energy and can run batteries down quick. The AAA we usually use in fairly long-lived devices that don't use energy very quickly. But they would be interchangeable. We could wire them into each other's devices and they would at least turn the thing on. The 9 volt's pretty different. The reason for these differences has to do with the chemistry inside the batteries, and that's something we'll look at in a later lesson. Car batteries have a voltage of 12 volts, which has to do with their particular chemistry. As you can see, they have lead in them, and that's different than the batteries we saw in the classroom, and we'll see that that gives them a different voltage. Our Van de Graaff generators routinely generate 200,000 to 300,000 volts. So you'd think they are very high energy devices. But they're not. As you saw in previous videos, I was willing to shock myself with them. So this difference between energy and voltage is very important. 300,000 volts sounds dangerous, but it wasn't enough energy to hurt me. So we're going to have to figure out that distinction. We discussed why it wasn't a large amount of energy in the previous lesson. If you don't remember, it's that although the voltage is high, the amount of charges that actually transfer are pretty low, so their product, potential energy, is pretty low. In this video, though, I want to talk about potential voltage and how it has to do with location. So in the previous lesson, we defined potential energy as being equal to the charge times the rest of the equation that has to do with where you are. And we said that different locations, different distances from this big positive charge would have different potentials. So if you bring a certain charge here, it has a different potential energy than it does here or it does here. So you've seen up till now in the class that if you drop something it has potential energy, that potential energy will be lost and it will be turned into kinetic energy. We can use stored potential energy to do work on something. And that's what happens in electric circuits. We use charges that are in one location and therefore have one potential energy. We let them fall to a different location, acquire a different potential energy, and the difference between them ultimately is the energy that goes into running the device. Now, this Van de Graaff generator is not a good way of powering an electronic device, because you remember what happens when I put my hand near it. A spark jumped. Well, what happened then? For a little while, all of the positive charge on the dome was gone. At that point, there wouldn't be a difference in electric potential in the two locations. So for powering practical devices, we need something that's always going to have a difference in potential between two different locations, so that we can allow charges to fall between them smoothly and have their potential energy converted into other energy. That's what happens with a battery. So in the case of this AA battery here, there's one chemical that's being oxidized, and its electrons are made available on the negative side of the battery. There's another chemical that's being reduced, and that means that it wants to take electrons in that come in through the positive side of the battery. So because these two chemicals are undergoing a chemical reaction, their chemical potential energy is changing. If we couple those reactions, we have electrons being pushed out here and pulled in there. And what that means is that until the battery starts to run out of chemicals, there'll be a relatively constant potential difference here. Electrons will be flowing out there and into there. And we can use that difference in potential energy to make electronics work. Here I've got 4 D cells, which have a voltage of 1.5 volts each. So how does this represent more potential energy for charges, and therefore charges going around the circuit with more energy? Remember, electric potential or voltage is the energy per charge, per coulomb of charge. Each of these has 1.5 volts. That means for every coulomb of charge that is transferred, we get 1.5 joules. So let's use these ping pong balls to represent a coulomb of charge. What would happen in the circuit? They start below the battery, and the battery actually raises them up, makes them have higher potential energy. That potential energy is then available to be released and used to do work. In that case, to make the charge move. Each cell can contribute 1.5 joules per coulomb. And you can gang the cells together. If, for example, I use 2 cells, you can see I've given this charge more potential energy. Therefore, we expect it to be able to do more work. So that would be 3 volts, 3 joules per coulomb. This coulomb, we're going to pump up all 3. Now it has 4.5 joules per coulomb. So we can actually add potential energies together, potential energy per charge, to give our charges the potential energy we want. We never want to give them too much, though, because then they might damage the system. So the meter's confirming that this 9-volt battery is indeed giving us 9 joules per coulomb. Each of our charges is given 9 joules. And that means it's good for sending charge through with a certain amount of energy. And that amount of energy is really good for things like a smoke detector and certain types of radios. And that's why we use this kind of battery. We use other batteries when we require other amounts of energy per charge. And each device is set up to work with a certain amount of energy per electron. Now that's not what voltage is. Voltage is energy per coulomb. A coulomb is more than 1 trillion electrons. So it's potential energy per charge, but don't mix up a coulomb with an electron. But the bottom line is voltage is a measure of how much energy each charge has. If you don't give it the right amount of energy per charge, it won't work right.